Hello. Oh, okay. Now it works. Okay. Okay. So it is my very great pleasure to be here today. My name is Leibny Paola Garcia Perera. I know it's a very, very long name. People usually call me Paola or Paola Garcia. So today we are going to talk about the current trends in speaker diarization. Let's do something like a kind of interactive. I like people to ask questions when they come to their mind. So if you have any question, just like please raise raise your your hand. Oh, there are still people coming, so that's okay. So well, we can start. So I come from Johns Hopkins University, and it is my great pleasure to be here today. So first of all, I have a disclaimer. So this is a presentation based on accepted papers at INTERSPEECH 2022. So if you see your name here, is that I borrow some of your slides and ideas. And there is a lot of very good work. And I really want to highlight what you have done. But first of all, let's see what is diarization. Diarization answers the question who spoke when in the recording. So in here we have a speech signal, and from this speech signal we can obtain the different speakers. In this case we have 3 different speakers: speaker 1, speaker 2, speaker 3, and we can see that it can be also, we can have also overlaps, and we get rid of the silences in between. But we cannot, or we usually don't stop only on the diarization, but we usually extend it to other downstream tasks, for example, ASR. Okay. But why is diarization so important? Right now, with the popularity of DNNs everywhere, we know that these meeting scenarios where you want to know who's speaking and what is the person saying, that is something that to be taken into account. If we have like this also patient-doctor scenario, if we have these very long recordings that would usually happen on children's speech. And I also learned a few days back that also happened in podcast. And if we have, for example, this cocktail party scenario when you are with your friends and you want to disentangle somehow who's speaking when. So that's why diarization is important. And I usually start these talks saying the metrics or how to define how a system, what the diarization system is good. And we have 2 main metrics. The first one is the diarization error rate, and the second one is the Jacquard error rate. The diarization error rate just sum up the different errors, the false alarm, the misdetection, and the speaker error, and is divided by the total duration of the audio. The Jacquard error rate, we take into account each reference speaker, and for each reference speaker, we might have also hypothesis speaker, and it is computed just with the false alarm, the misdetection, and the total of the union of the reference speaker and also the hypothesis speaker. And we sum up all of these Jacquard error rates and divide it by the total of them is just the app. Okay, with this in mind, we have to say that the lower these errors, the better. And now we are going to talk about the traditional diarization. This is the cascaded system. I usually call it the embedding clustering, but the community right now are calling it a cascaded system. So we have here the speech signal. This is the complete the complete pipeline. So from the speech signal, then what we want to obtain is what is called the RTTM, and it's just a list of, you can see here on your right, that this is just the list of different speakers and the timestamps. But well, the pipeline is as follows. The first thing that most people do is to have an enhancement stage. In this enhancement stage, we get rid of the noise. Then we have a voice activity detector to get also rid of the silences. And from this stage, we can have small speech segments from which we can obtain the embeddings. The embeddings are just the mathematical representation of these speech segments. And from these speech segments, we are going to compare them all versus all, and we're going to compute a similarity matrix. I need to learn how to use this, like the shown in here. And from that similarity matrix, we can do some kind of clustering. That means we are going to group together the speakers that the different scores that are similar. And from that clustering, we have to do the resegmentation. The resegmentation is just to refine the different boundaries for the different speakers. And if we want to get fancy, we can also apply what is called the overlap assignment. The overlap assignment is when we have two speakers speaking at the same time, talking at the same time. So, and in the end, from the clustering, from the resegmentation, and from the overlap assignment, we can get the RTTM, this nice list. This nice list, right, that shows us the different speakers and the timestamps. Okay, but according to our according to our pipeline, there was a breaking point, perhaps 4 years ago, with the BBX, and we have here the author of the BBX, and it is the variational-based hidden Markov model clustering, and it was a breaking point because before that we were using the I vectors, but after that this approach allow us to use the X vectors, and we have a same model like a hidden Markov model that is here. So we have 3 different speakers, and you can see that you can pass from one speaker to the other, and we can even stay in one speaker. That means that the speaker continues talking. And the nice thing of this approach is that you can model it using a single Gaussian per state, and the initialization comes from another model called the PLDA. So that was a breaking point because this new way of clustering that we have talked about before allow us to use DNNs. But then what happened? With the popularity of the normalization, we wanted to make it like kind of end-to-end. So we wanted to replace all the full pipeline with a single neural network. Okay, so we have just the speech signal and then a bunch of DNNs, and at the end the RTTN. And there is also change in the philosophy. The diarization is now seen as a multi-level classification. So for example, in here, we have the different segments or samples, and this new approach allows us to have 1, 2, or 0 speakers, or even more speakers, right? Whatever number we want. The only problem is the training that we are gonna use. So 0, 1, and two different speakers. And it's very natural to have here overlap. So we don't have to have the stage of overlap assignment, because in this approach, the overlap is natural. And the breaking point is what is called the end-to-end encoder, decoder attractor, that it can be used with variable number of speakers. So at the very beginning, what we had was just a single end-to-end model that need to have fixed number of speakers, but the encoder decoder attractor allows us to have a variable number of speakers. So it is very simple. So we have the let's say that encoder that can give us some kind of embeddings, and then from these embeddings we have the encoder decoder that is just a LSTM decoder that produce some kind of attractors that can be seen as the different clusters for the the speakers. So if we apply the dot product between the attractors and embeddings, we can produce the diarization results. But what is going on right now? Right now, this is what I want you to learn from this talk, essentially. So we have different systems. We have talked about the end-to-end. We have talked about the cascaded system. There is also another one called target speaker VAD. There are also some approaches that use multimodal data. And what about the unsupervised approach? We haven't talked about that one. We will see that one in the next slide. And also the self-supervised. And also the people are now worried about how to do everything online and how to really improve each of these parts. So let's see what is happening. First, we are going to talk about the end-to-end, the EEN, end-to-end diarization. So at the beginning, we were training the end-to-end system with just random chunks of speech. They really didn't have like anything to do with the actual way how people have conversations. So this approach is quite interesting. This comes from now on. We are just going to talk about the papers that are here. So this is like a lighting talk for each of these papers. So right now, what they are trying to do is how to create synthetic conversations that are closer to the real ones. That is including the pauses, the overlaps, all of these things. And you can see here in the results that there are very nice improvements if they include the fine tuning and also the statistics that we are talking about. These results are for Colholm and Die Hard 3. Okay, so this was one of the first approaches. And then what about getting the best of both worlds? So let's say that usually for the EEN, we focus only on very small segments because it is very difficult to train with long segments and distinguish the different speakers. So in here, what we have is that the people decided, these researchers decided to have small chunks of about 5 seconds. And with this 5 seconds, they can get some result and then can do some kind of diarization process, and then they can do some clustering and then kind of timestamps. But of course, this fixed 5 seconds was not the best option, right? So what they did next is what is called utterance by utterance. This utterance by utterance comes from the graph PIT-based voice activity detection. So in this case, the segmentation is not longer a limitation. So we can see here that is like a source separation thing where you have 2 channels. And with these 2 channels, you can distinguish the voice activity detection. And you can see that it can give you the one when it's a speaker is talking and 0 when nobody's talking. And also it can give you the utterance beginning detection. So it has some peak when it shows some peak when the speaker starts talking. Okay, and so this is relevant because if you can see overall the average diarization error rate, it improves a little bit, but it seems that for some cases it is better, right? So for example, for 6 number of speakers and so on. So these approaches were the main goal was to use them for long sequences, for very long audios. Okay. So now let's talk about embeddings. This is a nice one. So this reminds me to the I vectors a little bit because we usually use embeddings that are fixed, right, with no uncertainty. And this approach brings us back to a little bit to the I vectors where we can use some kind of uncertainty. And in this approach, what we have here is that the vector is like a floating vector, and it depends not only on itself, but also on the samples, on the different samples of the same speaker, but also on the samples of different speakers. And they have this global pairwise scoring that it takes into account this global approach, and also the local part of it. It's given by the end-to-end diarization. And finally, we get the label sequence. As you can see, it really improves the baseline EN approach, and it was done with a simulated NIST SRE10. And this is also a nice approach because it not only deals with diarization, but it also can do better things for speaker verification. And now let's talk about the clustering. The generic neural clustering that can be used with any chunk predictor. I just put it here just to put it somewhere, but it can be used with any types of chunks. So they use this RNN that can estimate the number of speakers dynamically during inference. And it can be iteratively optimized using a GRU. And these results come from Colholm. They also have some results on liver speech. And you can see that if you use this approach with a match condition and also with a mismatch condition, at least they get competitive results, or even better. And now the EN-EDA, so the encoder to decoder attractor. How can we really improve the encoder the decoder attractor? I think at the beginning I mentioned that it was an LSTM that made the attractor work. And in this approach, what they did was to replace that LSTM with a non-autoregressive approach, and a transformer encoder, and iteratively refine the system. And you can see on the right side, right, the different iterations from 1 to 4. That's what they used. And you can see how the different speakers get like different colors. So it means that it's working. They use the Colholm data set, and you can see a very huge, well, kind of huge improvement. Now let's talk a little bit about self-supervised. The self-supervised. So up to now, just like a few researchers have tried the self-supervised. In this approach, the self-supervised, they wanted to generate high quality embeddings without annotated data. So they look for the different segments of the same speakers, and they define, they maximize the agreement between the embedding vectors of two different segments of the same speaker. So we have here two speaker set Colholm. The rest is the PLDA. So that we have that is just like a scoring clustering baseline system. It has nothing new, but the good thing is that right now this new embeddings have no annotations, so we can get the segments without annotations, and we can see that they are very competitive with the X vector, with the let's say with the cascaded system, where we have like the X vector plus an LSTM. And we have this unsupervised with an Oracle VAD, and then we have the completely unsupervised approach. Of course, the unsupervised by itself, it didn't give like very good results because we need still the power of the voice activity detection. And now let's talk about the target speaker VAD. This is an extension of the target speaker VAD. At the beginning, the target speaker VAD wanted to do exactly the same thing that we do, diarization by itself, but it was very difficult because it was for fixed number of speakers. And now this is an extension of that approach. They compute frame level embeddings that are for target speaker detection, but also for speaker embedding aggregation. So they use a ResNet, and they also use the TS VAD and speaker extractor. They share exactly the same front end. And they also use, since they are chunking the signal by small segments, these target speaker embeddings can be updated. And they use the Ali-meeting eval for this approach. And you can see here that Since it is an online extension, it cannot be as good as the offline, but I think we are in the correct direction. Now let's talk about the clustering. This is a very interesting multimodal clustering. So we have the speech signal here, and from the speech signal, we can obtain a transcription. And what happens if this transcription we can recognize according to the role that each of the speaker has in the recording. So for example, in here, we have two roles. We have the student and the teacher, and then again, the student. Then we can guide the diarization. So apart from getting the different speakers, we can constrain the different segments to be of a specific role. So this is called the supervised text-based model to extract speaker roles, and it is a guide. It's a guide to the spectral clustering. So if you find that, let me go back. If you find that some of the segments have the role of the students, so you link them together. If you find that some of the segments belong to the teacher, then you link them together as well. But if they are not the same, well, you cannot link. Okay, so they use the UCC TAL data set, and you can see here, if you do have the audio only, you get some result. But if you have the text only, you get another result, which is not very good. But if you have both of them, then you have very good improvements. Then is it possible to do some clustering online? The answer is that we are in the correct direction as well. So this approach shows an interaction between embedding extractor and cluster algorithms. The clustering is what they call the clustering guided recurrent training. So they define some clusters and they compare them with the ground truth. And with this output, then is fed again to the embedding extractor. And then they have this truncated beam searching that it just looks for the path, the correct path for the different speakers. And they use iShell for this approach. And you can see, okay, this is, of course, is online clustering. You can see that there is some kind of improvement between two methods that they mentioned compared to the, there is an improvement between the two methods. Of course, they will never reach, well, right now there is no way they can reach the actual BBX, but yeah, this is also a nice direction. What about the backend? By backend, I just mean the part that goes after the clustering. So in this backend, what they were exploring was the multi-scale speaker diarization. So we know that if we have very small segments, what we're gonna have is not a very good embeddings, because there is a problem between the temporal resolution and the fidelity. So with this approach, what they wanted to do is to have like this multi-scale diarization decoder with multi-scale cluster initialization. So the clustering is initialized with a multi-scale in a multi-scale fashion, and then what they do is they make a comparison between the structured embeddings with the cluster average embeddings, and they just scale the weights with a 1D convolution applied to both based on this clustering. And at the end, they just have an LSTM to obtain the labels. And you can see here that the results are quite encouraging. So MSDD stands for the multi-scale diarization decoder, and A and B are just that they have some kind of color or not. Now let's go to the unsupervised part. So this is also the main goal of this work was to also tackle very long recordings. So they want to remove the part of the clustering and the post-processing, and they wanted to use just like a sparse optimization. So in here, I'm just showing you the cascaded pipeline, and also like some blocks resembling the embedding and the clustering, the post-processing. So in this approach, they wanted to get rid of this last part. So how they did that? First of all, they define a few things. They wanted this system to be agnostic to the language. They wanted to be overlap aware, and they wanted to be tuning free. So the things that we always want, right? But the way they did it was to replace the clustering and the post-processing with a sparse L1 regularized optimization. So here you have how they did it. So the hyperparameter optimization was inspired by the compressed sensing and linear algebra. And the embedding basis is computing just by using an L1 regularization over a local basis matrix. And they use this American Life podcast. So those ones are really, really long recordings. And you can see that the results that they are obtaining are quite here. All of them, well, if we can focus on the diarization error rate, that's quite encouraging, but also about the purity and the coverage are also good. Okay. Now let's jump to the online approaches. Online speaker diarization has also been difficult, and what we want is to address not only short recordings, but also long recordings. And this approach, what it's doing is to do it block-wise. So first they compute some kind of core samples, updating with some penalty function, and then they select some clustering samples from the core samples to help the PBX. So this can be also be seen as an extension of the BBX. And they solve the label ambiguity problem using the global constraint algorithm. So you have here the offline version of the BBX, and also the second one was the one proposed by Hitachi, and this one is the proposed version. Okay, so you can see that there is some kind of improvement as well. And now the multimodal part. So right now we are just seeing the audio diarization. But what happens when we jump to audiovisual? So right now we have two main approaches that we're going to explore. So this one is the MSD while, multimodal speaker diarization data set in the while. So it is a benchmark data set. It has rich real world scenarios. It has different languages, which is something super important. It has no over editions. It has overlap speech. It contains culture party scenario, and it also is. They also release the video and the audio. It is very important because it's different to what we have seen, to what we have seen before. For example, the box 11. And we can see here a comparison of the number of videos, the duration, the speech, and as I said before, the different languages that it has. So at the very end, we can see that it has multi-language. We can also see in the next table the diarization error rate and the Jacquard error rate for audio only, for visual only. If we have like two streams and then just combine them together, or if we use some kind of fused approach. So if we use a fused approach from the beginning, we can get better results. And now let's jump to the audiovisual end-to-end system. So in here, you can see like 3 different branches. This is a very nice audiovisual approach where the libs, the audio, and also the eye vectors are used as input. Okay, and in the end, we will have a nice diarization. So the end-to-end audiovisual diarization, they use the audio features, the multi-speaker lib, the region of interest, and the eye vectors. The classification output layers produce labels, and it can naturally handle overlap, speech, and non-speech. And the eye vectors are super important because they are used for alignment. And they use this MISP data. And similar to the previous one, you can see that there is some advantage of using the two modes, right? So we have the target speaker VID, we have just the visual approach, we have the audio visual without the eye vectors, we have the audio visual with eye vectors, and we have the audio and visual and with iVectors and the joint training. And of course, if we combine all of them with the overlap, we get even better results. And we can also use with the Oracle VAD and without the Oracle VAD. So the takeaways of this talk, I hope you enjoy it. I thought, well, I think there's a lot of material here, but the takeaways is that EEN and BBX and the Target Speaker VAD are still good solutions. Most of them right now are following the online versions, so they are transforming to streaming mode as well. We have also these unsupervised and self-supervised methods that were proposed. Some of the methods deal with long recordings, like the podcast. The new methods are out of the traditional. For example, the one that we saw about the sparse optimization and the one that we saw about the role labels. We also have online diarization is becoming feasible with very good results. And some approaches are still on simulated data, but some others are on real data. And what research directions are important? So for what we saw, and also this has some of my opinion, and I think that the multimodal diarization, text, video, audio are important. We haven't talked a lot about the speaker imbalance. What if we have just a speaker that talks for, let's say, 3 seconds in the whole recording or 4 seconds, right? What about the online diarization? It is still an unsolved problem. We really need to tackle real world data. What about the long recordings, like children's speech? I know that we have talked about these long recordings like the podcast. And we should consider speech separation algorithms that combined with diarization can improve the overall performance. And diarization is only part of a very more complex scenario. For example, we also have to think about downstream tasks such as the ASR or others. And I think that's all. Thank you.
Okay, actually, this scheduled session time was over, but we can have 1 or 2 quick questions or comments. Please use the microphones.
Thank you very much for the talk. It was a nice overview. Just a general question. Are there any sort of tasks that are sort of unifying the community that, general challenge problems that are being offered to the diarization community to work on together?
Yeah, yeah, we have Box Converse and we also have Die Hard. Yeah, we also have another one from Facebook. So we have challenges here and there. So it's not a problem about challenges, but it's also about how to really deal with the real data outside the challenges. I think that one that really tackles most of the different conditions is Die Hard, right? That it has like subcorpora. Yeah, and it has restaurant and it has also one single speaker recordings, but not all of them have those characteristics. Mm-hmm. Yeah.
Okay, any other question? Okay, thanks, speaker.
Thank you. Thank you.
And we're gonna start at 12:50 for the another survey talk. Thank you.
Okay, it's time to start now. So the talk now here is privacy in speech technology, and my name is Tom Bäckström. I come from the Aalto University in Finland. There. So just a kind of light introduction here. That just looking at the number of papers at INTERSPEECH about privacy, you see that for like 5 years ago, or before 5 years ago, there was hardly any papers at INTERSPEECH about privacy, and after that, it has really jumped up to this 13 or 14 papers per year, and that's now really kind of papers with privacy in the title, or in a session with the title of privacy. And that also kind of aligns with when we formed the special interest group in 2019, and then this voice privacy challenge started in 2020. So it's a rather like young activity, but really taking up speed rapidly. So I'm going to talk about after the introduction mainly about objective privacy, but also subjective privacy. And the objective privacy refers then to the actual level of privacy in a system, and the subjective privacy refers to the experience people have about privacy in a system. So you know that many people are afraid of privacy things, even with secure systems, and some people are not oblivious even if the system would be dangerous. So that's the subjective side. But let's first look at the objective privacy. So the actual level of privacy. So the most common threat model here is really this kind of a cloud service based thing. So this is an example. I mean, the specifics of the threat models are different from case to case, but typically we think about a cloud model or cloud service, where the user wants to access some services in the cloud through his edge device or mobile device or smart speaker or something. But then as a kind of byproduct, the service provider also has some other services it performs. For example, now kind of search engine might do have advertising functions involved when you access it. So this is kind of from a user's perspective, so it's outside the user's control, so then that makes it undesirable. And the main kind of approach to that is that so this undesirable service, we want to somehow prevent that, and we do that by limiting the amount of data which is sent from the edge to the cloud service. And if we limit this amount of data here, then this should be difficult or impossible, this additional threat here. But before going to the actual solutions, let's look at a bit of vocabulary here. So this is now a kind of example sentence. I'm now using text as an example, although most of the work at INTERSPEECH is about the acoustic side. Anyway, so this is a sentence, and if you do anonymization or de-identification, that means that we remove this identifying information about the person, so Jack, and corresponding suppression would be to remove any other sensitive information like health information here. Pseudonymization again is then replacing the sensitive information, in this case the identity, with some other valid similar information. So then in this case the sentence remains a valid sentence, and it has similar structure and properties as the original, but it's just kind of anonymized or pseudonymized. It's very careful task of choosing how you choose that alternative name. So if you really have to pay attention how you choose the pseudonymization, because if it's always for example, if my name would always be assigned to Rudolf, then of course I would be identified as Rudolf. so it's not anonymous anymore. But then obfuscation refers to basically adding noise. So all of these are actually also some sort of obfuscation, but just to point out that it is a different thing, the obfuscation. Disentanglement refers to separating the different categories of information. Now here is like the original, like the anonymized text, and then the identity and health separated. And the encryption is the obvious transform then. But then the actual models here, this is kind of in some sense a parent model to most of the other models. So here we have that this trusted model. This is the task which we want to do, and this is the undesirable threat which we have as well. So the kind of the trust part, so the decide service works as any kind of normal speech system does. We have an edge device which sends some features to the cloud, and we do that service which we want to do and optimize it with some loss function, and by modifying the parameters of the features and the kind of decoder. But then at the same time, we have here a undecided service, so the threat here which tries to extract some private information from the features which are sent by the edge device. So it tries to that, for example, now kind of determine health information of the user here, and then optimize its model also by training back propagation. But now then the same kind of result here goes also to the trust model part with a negative sign. So this part trains features such that we can do this service, but are unable to do this threat model. And so kind of I'm going to here present not only INTERSPEECH paper, but like a bit of also other important papers. So this kind of trust and threat model was really championed by Alexandru Nelus and his supervisor Rainer Martin, and his doctoral thesis was kind of recently presented, and also his transactions paper, which contains most of the important stuff. Now at INTERSPEECH here, we have 3 papers, or at least 2 papers, which are really in this category. So the first one here is the gender ambiguous voices. So really trying to generate voices without gender. And then kind of, and then the sensitive word recognition and replacement in the second one. This third one is bit different. It kind of looks at what information neural networks can memorize, or what sensitive information they can memorize. But going from anonymization to the more specific, so it's the speaker anonymization and pseudonymization task. This is actually a more common task, so we're really trying to de-identify speakers. And the typical approach here is that we have the analysis block, which produces the X vectors, so that's the speaker identity, and then the other part is all else, so features for everything else, typically something like F0 and the posterior, so phonetic posteriorograms. And then by replacing this speaker ID with some other speaker ID, you can then resynthesize the sound such that it's some different person. So this is a basic voice conversion task. And this was also in the voice privacy challenge 2 years ago, the task. And this is now from the final results, or the main results of that challenge. We see that there was quite a few candidates here, and the success means that you are above 50% error rate, so that we are unable to identify the person. And we see that some like five or six candidates came up to above 50. And that's in the ignorant mode where the attacker does not really know much about the system. But when there's some information about the system available for the attacker, it becomes immediately more difficult, and even the best one here had only 39.7 like that as their equal error rate. So this is just to demonstrate that the state of the art can currently solve some kind of limited problems in this voice privacy type of scenarios where we try to anonymize speakers, but in the more complex cases, it still fails quite a lot. And kind of, I really recommend that you go and look at the voice privacy challenge. Now, these results were from 2 years ago, but now tomorrow and on Saturday we will see the new results of this year's challenge. And here are some papers of the previous voice privacy challenge. I don't want to spoil the result of that challenge quite yet. This year's challenge. But kind of at this year's INTERSPEECH, we did have 3 papers in this speaker anonymization task. The first one was slicing. So the idea here was to cut up speech samples into shorter segments such that you can still train ASR, but then the speaker recognition becomes difficult. And then the second paper looked at the kind of performance of speaker anonymization in unseen conditions, and of course it does degrade, obviously, and it improves when you have more training or more varied training data. But really the value, I think, of this paper was to demonstrate in which kind of conditions or what types of information which is the cause for this problem. And then kind of the last paper here looks at the kind of the phonetic posterograms, how much private information is leaked through the phonetic posterograms. So even if the phonemes are supposed to be like anonymous, there's actually information leaking through from there. The next category of methods is here cryptography. And here the typical threat model, of course, so cryptography itself doesn't have a threat model, but the typical threat model where this cryptography is applied is the low mutual trust scenarios, where, for example, health information, where you want to analyze whether the patient has a Parkinson's or something, kind of, then the patient might not want to share his health information with anyone. So they don't want to send it to the analyzing service, but also the service might not want to share its model with the edge device. It's can be a very large model, which is kind of difficult to share, but it can also be proprietary, such that they don't actually want to share the edge device. So then here's an example of homomorphic encryption approach, where the edge device encrypts all the features it will send to the cloud, and then the cloud does the processing in an encrypted domain. So the cloud can do this processing on the signal even if it never sees clear text signal. So this is a bit of math magic happening in the background. It's really a beautiful solution to this problem. So none of them, no information is leaked, but of course there's a penalty, and that's the complexity and bandwidth requirements. So a bit depending on what kind of approach you choose, the kind of bandwidth you need to, the amount of information really is megabytes or terabytes to do one analysis, and also the computational cost increases exponentially with the complexity of the problem. And there's been quite a few papers now about this. So I think Patricia Thane was one of the first ones to apply apply this on speech processing type of scenarios 2 years ago, 3 years ago at INTERSPEECH. There's a few others as well, and now yesterday we had Francisco Bäckström's paper about secure multi-party computations. So they are actually quite close to already achieving a realistic scenario or a realistic application of this kind of solution. More categories. There's the distributed learning. Here the idea is that we don't. So the problem is always when we send stuff to the cloud. And the reason we want to the cloud really wants to have data is to train their models. But now, if we would do the training of the models already at the edge, then we would never need to send the actual data to the cloud, but only the model updates. So this is also a kind of a nice solution problem, because the private data is never transmitted. Of course, those, like we said, we know that neural networks can contain private data. So this is, it's not a perfect solution, but so it's just a form of anonymization or obfuscation. And also here, there's quite a bit of papers, really has been a popular approach. I won't go through all of them. I'll share these slides on my LinkedIn page and other places, so you can go look at these. But there's quite a lot of work in these areas. I think one of the principal, or two of the principal challenges in applying distributed learning. So one is really practical, that you really need to simulate this kind of system. I mean, here I have only 3 devices, but typical system, if you think about the cloud system, would have thousands or millions of edge devices doing training. And now if you want to simulate that for a research paper, it actually requires quite a bit of thought how to implement this in a reasonable way, such that you can train networks with million edge devices in parallel. The second question, which I found quite challenging with these distributed learning scenarios, is really the accurate use case modeling. So who wants to do this? Who gets what information? So you really need to think that through and spend lots of time think what application are you targeting. For example, a bank application. That's one of the few where I see this as a good solution. And now also at INTERSPEECH, there's again 3 papers which address this issue. So the first one here was like acoustic sensor networks, where you do speech enhancement type of things in a distributed network and clustering. So in a privacy-aware domain. And then the the next one was kind of ASR models, also looking at the updates, and then use finally this speech emotion recognition with a federated learning system. Local environment is another completely different category. Here you see that this is actually what I experienced at home office when I was working at home next to my wife, and we both had Zoom calls at the same time. Of course, when I talk, it will leak to her call, and when she talks, it will leak to my call. So that's not only an acoustic problem, like a quality problem, but also very much a privacy problem. If I say something sensitive, they will see it in the other call as well. But it works in both ways. That also the loudspeaker sounds will disturb me, and I would hear private information from the other call. So there's now on the microphone side, so the speech enhancement side, I'm aware of only one one master's thesis actually my guidance made, but on the loudspeaker side, there's already work for quite a while in this sound zones. So how to create private sound zones where different spaces in the room receive different types of private information. And also, just shortly, when you are in these distributed acoustic sensor networks, when multiple devices collaborate, you also need to look at access management. I won't go into that now more than that. For evaluation and metrics, of course, our primary interest is privacy, but and that's also the most difficult part. It's really hard to know. So typically, there's a kind of adversarial models trying to extract some private information from the supposedly private features, and if the adversarial model fails, then we say that it's a private some sense. But that's not a theoretical proof. It's just that our model was not good enough to extract that private information. The other evaluation metrics are utility, quality, and resources, and those are pretty standard kind of metrics. And just as a practical example from the voice privacy kind of challenge, for the previous one, they had used speech naturalness, intelligibility, and speaker verifiability as their these metrics. And here, naturalness is then the quality, and intelligibility, the utility, and verifiability, the privacy metric. Now, final thing from the objective part is the differential privacy. This is a rather technical topic, but the main idea here is to try to get some science into this privacy evaluation. So kind of it gives theoretical tools to to assess what is the impact of the group size. So if you try to identify a person out of 10 possible persons, or if there's 1 million persons out of which you are choosing the speaker identity, it makes a big difference. And also, if we can narrow down the number of possible speakers down from 1 million, let's say we know that the gender of the speaker, we already narrowed down the number of potential speakers to half, and also the confidence interval. So the differential privacy theory addresses that type of things, and typical solution here is then to add noise such that those the ability to narrow down the speaker reduces. So these are kind of rather technical things, but really important. So I'm really happy that we now have the first papers in speech about differential privacy that I'm at least aware of, and they are all from this year. I don't think any of them were in INTERSPEECH, unfortunately. Finally, a bit time left. So subjective privacy. So this really is about how people experience privacy. This is now the work here is rather colorful in the sense that we are like isolated islands of very different types of works. So I don't have possibility to go through them in detail. But first of all, my own team's work about perception of privacy cues. So imagine, for example, if you go to a cafe and talk with a friend, how private is that? And what acoustic cues indicate to you the level of privacy there? So that sort of questions what this work addresses. Now, acoustic privacy can be thought of in a very different manner. Here in this paper down here, they looked at like hospital patient rooms with multiple patients. So kind of what happens with privacy there. That's a very sensitive question, even if it's not really a technological solution, but kind of practical acoustic solution or problem. There's been papers about kind of how much smart speakers are used and how that correlates with the user's privacy preferences. So of course, people who are scared of privacy, they tend to use less smart speakers. And that's really important for now for the manufacturers to understand this. A very different approach or question was trust in speech. So some people tend to distrust virtual assistants, and then they try to detect that from the acoustic signal. So that's also important with very little work done around it. Final thing here is the user interface design. So Birgit Brüggemeier has worked on these chatbots, and then they had kind of this the typical way to display a chatbot. There's a kind of path of different questions and answers, and then they had two options of either this privacy aware option or the kind of control option, and they show that if you do bit of nudges, if you ask questions related to privacy, people will actually understand that the privacy is better in the system. So you really have to do privacy design at all levels in the system. Okay, conclusions and outlook. So first of all, the challenges. There's plenty of them. So first of all, one of my really biggest worries is that privacy is only, so the privacy metrics are only as good as our adversarial models. So there's no guarantee that there wouldn't be some more advanced adversarial model which wouldn't still be able to extract some private information, even if the model we tried was unable to find any private information. And the kind of that also relates to the next question here is that if we remove, for example, now health information from the acoustic signal, the text itself can contain health information, and speech rhythm could contain kind of health information. So there's lots of leaks into different channels in the speech which can contain private information, and it's really hard to really specify where the sensitive information lies. Very different issue is that especially earlier, I felt that privacy was often seen as a cost to business rather than a gain in quality, which is somehow paradoxical. I mean, if you make better privacy to a product, it is a better product. So you will have a good product if you have good privacy. Of course, it kind of includes lots of work, added work also, but that's with any quality improvement, you will have more work. Final thing is something which I haven't seen anyone talk about. I'm the only one who ever talk about this. Is this individual character of privacy? That we treat privacy as an individual thing, but speech is always about the dialogue. Even here, when I talk, I have an audience with whom I interact. So you become part of the speech. So how could the privacy of the speech be ever evaluated only for me? You would have to be included. This speech is recorded and kind of will be on the internet, but no one asked your permission for that. I think that's somehow strange. I'm fine with that in this particular scenario, but overall, we really should think about shared ownership models in speech because of these privacy issues. But we don't have really any tools for them. We don't have any kind of theoretical framework in which to talk about shared ownership. But the outlook, I think, is encouraging. Research activity has grown exponentially. This really, like 5 years ago, there was hardly anything, and now we have really a solid base to work on. And also the awareness of the need in the community is growing. That now I feel that anyone who starts a project, they will have to think about privacy as well. Or they know that they should think about privacy. And like 5 years ago, I was really afraid that in speech we would have some similar scandals like the Cambridge Analytica or Megaface scandals. But now I feel positive that we actually might avoid that with some luck. We are kind of, if we stay on the current path, then we have a good chance of avoiding big scandals. And because this is a very young research area, there's really a lot of room for new innovations, and so it's a good place to come to do more research. Yes. So credits. I just quickly wrote up the first names that I could think of with whom I've interacted about privacy. There's probably many more who I'm forgotten, but really there's been quite a large community already. And final advertisement. So tomorrow starts the symposium on security and privacy, together with the Voice Privacy Challenge. And then I also invite you to follow the special interest group, especially the webinar series has been quite popular and nice. Yes, thank you. That's all.
Okay, we can have 1 or 2 quick questions or comments. Okay.
You mentioned potential scandals. In the speaker verification community, there's a lot of work on spoofing and things, and they involve some really sophisticated assumptions about really sophisticated capabilities on the part of the spoofer. Are there known examples, at least in the speech community, of there being a successful attack by some very sophisticated actor?
So I know that there's multiple kind of crimes committed with deep fake voices. I'm not sure of the level of some sophistication of those, but I had it earlier in the slides, but I had to take it out because of time constraints. But there was a bank heist of 10 million or 100 million USD, which they got with the deepfake voice. They sent a message to the big boss's secretary and kind of they got the money. So that's but kind of I tried to focus here also more on the privacy side and less on the security side. It would it's also a big topic, so there should be a separate talk about that.
Okay, any other questions or comments? Okay, actually we have just 7 minutes for the next session, so we can stop now. So thanks, speaker, and
Thank you.
thank you for your participation. Okay, thank you.